Hello and welcome to another EECS 203 Discrete Math podcast. Today we're going to be covering three subjects: Big O, Big Omega, and Big Theta notation. They're all kind of similar, but I think you'll get the idea when we get going. So the first one we got is Big O. Big O, a function f of x, is Big O of g of x if some constant c times g of x is greater than or equal to f of x. So that means that if you have the absolute value of f of x, it will always be less than or equal to this constant times g of x, the absolute value of g of x, for all x greater than k. So big O is kind of like upper bound of a function. So it's g of x in this case is some function that's always going to be dominant over f of x. It's always going to be bigger than it. Next we got big omega. A function f of x is big omega of g of x if some constant c times g of x is less than or equal to f of x. That is, if we have the absolute value of f of x, it will always be greater than or equal to this constant times the absolute value of g of x for all x greater than k. Big omega is like a lower bound to f of x. So in this case, g of x will always be less than f of x, or f of x will be the dominant function. So you can always think of it as a lower bound to the function. Next we have big theta. A function f of x is big theta of g of x if some constant c1 times g of x is less than or equal to f of x, and some constant c2 times g of x is greater than or equal to f of x. So basically c1 times the absolute value of g of x will always be less than the absolute value of f of x, which will always be less than c2 times the absolute value of g of x for all x greater than k. So big theta is kind of like big O and big omega combined into one function, because you have both the lower bound when you multiply it by c1 and an upper bound when you multiply it by c2, making big theta kind of like both of them in one function. Here we have some typical functions that you will see for any of the big O, big omega, big theta notations. You'll see permutations of these, and these are not all the functions that you have, but this kind of gives you an idea of the spectrum that you will see. If you have functions that are growing very, very slowly, you might use something like the log n or just straight n functions. Because as you can tell on a scale, these grow quite slowly and are perfect for binding slow-growing functions. On the other hand, if you have something that grows incredibly fast, you can use something like n factorial or 2 to the n, because these functions you can see grow quite quickly. And you have other functions in there like n squared and n log n to give you a range of functions that you can bind. And like I said, these are not all the functions out there, but you can, any function that you can find binding some other function you can use. Here we have, this is a demonstration of what I was talking about earlier when I said when x is greater than k, because as you can see, you have the function f of x, and f of x does not stay within the bounds of g of x on a small domain. It goes under it at first, then shoots over top of g of x. It is not actually bounded by g of x at the beginning of its domain. However, once it hits x naught, it starts trending to follow g of x as a function. So at x naught is now bounded by g of x on both sides. So as long as you can identify this and pinpoint where this happens, you can say, well, f of x is big theta of g of x for all x greater than x naught, since x naught's the first point where it actually starts being bounded by g of x. all the notations we've covered so far have some algebraic properties. So first we have the additive property. So if you have f1 of x and f2 of x, and they are respectively bounded by c1 times the absolute value of g1 of x plus c2 times the absolute value of g2 of x, then then you can combine the functions or add them together, and you have f1 plus f2 of x, and it will be big O, big omega, whatever, of the max of the two binding functions between g1 of x and g2 of x. So if you have something like n squared and n log n from the graph that we had earlier, n squared will clearly be a bigger function, or the dominant function in this case. So then f1 plus f2 of x would be big O of n squared. Additionally, we also have our multiplicative properties. If you have the f1 of x and f2 of x, and they are again bounded respectively by c1 times the absolute value of g1 of x and c2 times the absolute value of g2 of x, then you can multiply the two functions together, and when you do this, you get f1 times f2 of x. In this case, the function will be big O of the two binding functions multiplied together. So you will have g1 of x times g2 of x. This is a lot simpler, at least in my opinion, than the last one, because multiplying is easy, and sometimes it's not always the most easy thing to figure out which function is dominant over another one. So this just kind of gives you, here we have f of x equals x squared plus 4x plus 17, and we know that this is less than or equal to 3 times the big O of x squared. And we know this because if we have x squared plus x squared plus x squared, it will always be greater than or equal to f of x, which is x squared plus 4x plus 17. This is because 4x plus 17 is not growing as quickly as x squared plus x squared, which are in your big O function. So you know that your big O value will in fact grow faster than your f of x value, showing that f of x is indeed bounded by x squared. So here we have adding two big O notations, n log n squared and log n of n squared. So we need to know the big O notations. So first we have n log n squared, and its big O notation is n squared times log n quantity squared. Next one we have the log n squared, and its big O notation would be log n squared. Since we are adding these together, we need to take the max of the function. In this case, it's pretty straightforward because we have n squared in both terms, log n in both terms, but one of them, log n, is squared. That means that this function is going to be larger on a greater domain than the other function, meaning this is the dominant or higher order function. So n squared log n squared will be the big O function for the addition of these two. So let's take another example. If we need to find big omega of x to the third minus x to the third plus 5x squared plus 13. Since the x to the thirds cancel out, we now have 5x squared plus 13. So this being a simple polynomial, you just have to find the highest order function in the polynomial, which is 5x squared, and 5x squared is going to be bounded by its trending part, x squared. So 5x squared will be big omega of x squared, and since it is the highest order piece of the polynomial, it will set the binding functions for the entire equation. So now we're going to find big theta of 3x squared plus 8x log x. this is going to be x squared because in this case we have a polynomial piece of 3x squared, which is going to be big theta of x squared. And then we have the piece 8x log x. Since we're adding them together, as we did earlier, you have to find the higher, or the dominant function of the two. So 8x log x is going to have some function of log in its binding function. Since log grows incredibly slowly, as we saw earlier, then our big theta of this equation will be x squared. And that's all we have for now, so I hope you enjoyed the video, and come back for more as we release them.